Designing the backend for a digital wallet requires engineering for extreme volume, under zero tolerance for error. The system we are building must accurately process exactly 1 million financial transactions every single second. To understand how a system handles that kind of load, we have to look at the architecture through a post-mortem lens, starting with the single most common operation. Everything begins with a core API endpoint, the command to transfer a balance from one user to another. Look closely at this REST API payload for that transfer. Notice the data type assigned to the transaction amount. It is formatted strictly as a string. You will never see a float or a double used here. Floating point variables are banned in financial systems. Different hardware and protocols serialize floating point numbers in slightly different ways, and in a distributed system, those discrepancies introduce catastrophic rounding errors. When dealing with money, precision cannot be hardware dependent. That strict typing is the first of 3 uncompromising technical constraints for this architecture. The system must maintain 1 million transactions per second. It must guarantee 99.99. The dollar leaves node A and moves to the routing service, waiting to be deposited into node B. Now watch what happens when we inject a simulated crash into the routing service, right before it can communicate with node B. The money is gone. The deduction at node A succeeded, but the deposit at node B never occurred. By failing in transit, the system permanently deleted a dollar from existence. Standard CRUD operations and isolated in-memory updates operate independently. They are technically incapable of providing the atomic guarantees required for distributed finance. The traditional textbook solution to ensure transactions happen atomically across multiple nodes is the two-phase commit, or 2PC. It locks both databases, prepares the transaction, and only commits if both nodes are ready. We have to disqualify 2PC immediately. Holding database locks open while waiting for network hops destroys throughput. If a node delays its response, the locks stay active, the queue backs up, and processing 1 million transactions per second becomes mathematically impossible. To maintain velocity, we abandon the safety of native database locks. We move the responsibility for consistency out of the database and directly into the application layer. This diagram illustrates a pattern called TCC, try, confirm, cancel. In the first phase, the try phase, the application deducts $1 from account A, but issues a no operation command to account C. This creates a temporary imbalance. If you tally the system right now, it is missing $1 overall. If the subsequent confirm phase successfully credits account C, the ledger balance is out. But if the credit fails, the application triggers a cancel phase, a programmatic safety net that executes a brand new transaction to manually refund the dollar back to account A. This introduces a fatal edge case, out-of-order execution. If network latency causes a cancel command to arrive at a database before the initial try command even gets there, the database will attempt to refund money that was never actually deducted. To prevent out-of-order corruption, you must build a phase status table. This mechanism tracks the exact lifecycle state of every single transaction, ensuring the application knows exactly which phase has been executed and which must be ignored. Achieving massive scale requires a heavy trade. You sacrifice native database locks, take on application-level complexity, and manually trace every failure state. Even with perfectly tracked transaction states, this design still fails the ultimate test. An external auditor demanding mathematical proof of how a user arrived at their final balance. Standard databases overwrite old data with new data. Reading a final balance of $50 from a standard database row provides zero evidence of how that $50 was calculated. The history of the money is completely erased. The solution is an architectural principle called event sourcing. Under event sourcing, the current balance is never treated as the source of truth. It is treated only as a temporary view of historical facts. This diagram shows how event sourcing physically separates requests from records. A request to transfer funds is simply a command. When the system validates that command, it generates an event, an immutable, permanent record that the transfer successfully occurred. The state machine operates by sequentially processing this immutable log of events. It calculates the user's available balance in real time by adding and subtracting the exact sequence of historical facts. Because these events are immutable and the history is permanent, the entire timeline of the wallet becomes a repeatable mathematical operation. This is the basis for perfect reproducibility. During a forensic audit, you can intentionally delete the current state database entirely. You prove system correctness by replaying the event log from zero, proving that the exact same balance is recalculated every single time. In a valid digital wallet, state is a deterministic calculation derived from an immutable append-only ledger. This makes the account history verifiable by design. We now have an immutable event log, but we still have to process it at 1 million transactions per second without creating a massive network bottleneck. The solution is localized storage. The system writes commands and events directly to local, append-only files, utilizing memory mapping to exploit the extreme speed of sequential disk access. But localized storage introduces a critical vulnerability. A physical hardware failure permanently destroys the financial history of every user assigned to that node. To safely distribute and protect the event log across multiple machines, we implement the Raft consensus algorithm. This animation illustrates the specific role of the Raft leader. The leader accepts a command, validates it, and instead of just saving it locally, proposes the resulting event outward to multiple follower nodes. The system operates on a strict rule of quorum. The state is only officially updated after a majority of the follower nodes safely acknowledge receiving and storing the event. There is one final operational bottleneck. Millions of users constantly opening their apps to check their balances will flood the system with read requests, which threatens to overload the consensus group. To solve this, we introduce Command Query Responsibility Segregation, or CQRS. This architectural pattern physically separates the read-only paths from the heavy transaction processing write paths. Scaling a globally consistent state requires fiercely protecting the write operations behind consensus, while offloading the massive volume of client reads to asynchronous CQRS nodes. We can now combine all of these components into a single end-to-end walkthrough of the completed, massively distributed digital wallet architecture. The Saga coordinator issues a debit to partition 1, which replicates via Raft and acknowledges. The coordinator then pings partition 2, which runs its own Raft consensus to commit the credit. Finally, read-only nodes process this through CQRS, updating the client via WebSockets. Compared to utilizing a standard relational database, the complexity of this system is extreme and unforgiving. Bypassing database locks, relying on Saga orchestration, and enforcing Raft consensus are not stylistic choices. They are strict mathematical necessities for operating at this scale. This highly opinionated, event-sourced architecture is the only proven way to successfully process 1 million transactions a second, while surviving the intense scrutiny of a forensic audit.